Hello, welcome back to the lecture series on abstract magic theory. So, we already discussed the properties between improper Riemann integral and the Lebesgue integral. In fact, we have seen that if we have given measure space x and we have a function f from x cross j to r. This function where j is interval, it's a subset of r. If this function is measurable for all t belongs to g, and the partial derivative of this with respect to t at the point t naught exists. Also, this partial derivative is not partial derivative, that difference quotient dxt at t naught that we have seen, it's equal to f of xt minus f of xt naught. By definition, it's equal to this divided by t minus t naught. If this thing is dominated by some integrable function g x for almost all x's, then the partial derivative defines an integrable function, that this function is an integral function at x naught, and its integral is equal to limit t approach to t naught f of xt minus f of xt naught divided by t. This we have seen, t minus t naught dx. So limit of integral with respect to t is equal to the integral of the limit, but the integral of this limit is actually the partial derivative. So therefore, if we have the following two properties of the function, measurable functions. First property, suppose this partial derivative exists, d f xt with respect to t. Suppose this exists for all t belongs to the neighborhood v of t naught, and there is a function g which is integrable, non-negative integrable function, such that mod of d f xt divide del t, this is dominated by such function g which is non-negative and integrable for all the t belongs to u, where v is the neighborhood of t naught, neighborhood of some particular point, say t naught. Then we can apply this theorem. Then we can see that the integral of limit is equal to limit of integral. Okay, let's apply this theorem to evaluate the following integral that we call the Euler integral. So we have following theorem. Either, okay, and this is the statement is this: we have the integral 0 to infinity e power minus x square dx is equal to root of pi divided by 2. Okay, so this will see that this integral is equal to root of pi by 2 using the Lebesgue integration. Prove. First we see that the improper integral exists, and then we can conclude that its Lebesgue integral also exists because it's a non-negative function. So improper integral of e power minus x, existence of improper integral of e power minus x square is same as the existence of the improper integral of mod of e power minus x square, and from this we can conclude that the Lebesgue integral also exists. Since we have this e power minus x square is less or equal to e power minus x, okay, for all x greater or equal to 1, you can easily verify this, because whenever x is greater or equal to 1, x square is greater than x, so minus x square is less than minus x. So that's a straightforward. And the integral 1 to infinity e power minus x dx, this integral exists. You can easily verify, we can easily calculate this integral. So therefore integral 1 to infinity e power minus x square dx also exists. So this implies integral 0 to infinity e power minus x square dx as improper integral. They exist 0 to 1 because this equals 0 to 1 e power minus x square d square, and here we don't have any singularity because we have finite range of integration and the function is continuous throughout. The function does not have any singularity in this range, and plus this is 1 to infinity e power minus x, and this we have seen this also exists. So therefore the integral 0 to infinity e power minus x square exists. Okay, this implies integral 0 to infinity mod of e power minus x square dx also, because it's the same as mod, because this function is a non-negative function actually. This also exists, which implies the Lebesgue integral e power minus x square d lambda exists. Lebesgue integral exists. So this function is now Lebesgue integrable, and the Lebesgue integral and the improper integral are same, and these two integrals are same. E power minus x square dx is same as integral e power minus x square d lambda. So both are same. This is over the set 0 to infinity actually. So you can write here the set 0 to infinity. So we find its value as Lebesgue integral, okay, and this is same as improper integral. Now for this we take two functions in order to find its Lebesgue integral. What we do, we define two functions. Consider the real valued function as an R. Consider the real valued functions on R, which we define by defined by the function. Let's say f of t is equal to integral 0 to t e power minus x square dx, e power minus x square dx whole square. And let's define another function g of t, which is equal to integral 0 to 1 integral 0 to 1, the function is e power minus t square times 1 plus x square, t times 1 plus x square divided by 1 plus x square dx. Let's take these two functions. It's t square here, okay, this is t square. So both are functions of t, because if you integrate this with respect to the variable x, then you take the limit 0 to it will be the function of t, and if you integrate this with respect to x, then take the limit 0 to 1 of x, and you will see this will be the function of t on it. So both are functions of t. Now we apply the fundamental theorem of calculus to find f dash t. So this gives by fundamental theorem of calculus, okay, fundamental theorem of calculus. This f dash t is equal to twice integral 0 to t e power minus x square dx, and then we have the differentiation of the integral function, which here we apply the fundamental theorem of calculus. Actually you are applying fundamental theorem of calculus and chain rule simultaneously, okay. First you apply chain rule, you integrate this function power n, its power down power minus 1, then to integrate this you apply the fundamental theorem of calculus, and its integral is equal to e power minus t square. So this is equal to twice e power minus t square integral 0 to t e power minus x square dx. This is your f dash t. Okay. Now for g, what we do for g? We have another function g here. So for this g, we will see the partial derivative of the integrand, which is e power minus t square 1 plus x square divided by 1 plus x square is here, not t square, 1 plus x square. We will see its partial derivative exists, and that partial derivative is bounded by some integral function over any particular subset of R. Okay, let's see this. Let's for g we observe that for g we observe that mod of del t of the integrand, which is equal to e power minus t square times 1 plus x square divided by 1 plus x square. You are integrating, you are differentiating this function with respect to t. Okay, is that clear? So you are treating this x as constant. So what's the integration, what's the differentiation for t square? It's e power minus t square, and this is your constant here, 1 by 1 over 1 plus x square. This will come out. Okay, so e power minus t square times 1 plus x square, then you take the differentiation of inner function, which is equal to minus t square times 1 plus x square, and that is equal to minus t times 1 plus x square, and you will see these two will go, 1 plus x square and 1 plus x square. This is equal to minus twice t, and it's e power minus t square times 1 plus x square. Okay. Okay, and this one you are taking its mod. Actually, it's everything is on a mod. So this is equal to twice mod of t into mod of e power minus t square times 1 plus x square. 1 plus x square. But what's this? This one, it's the power e power minus t square times 1 plus x square. Is it less or equal to 1? This one? Oh, so it's a negative power. It's a negative power. So it's actually 1 over e power some positive thing. So that's always less or equal to 1. So it's less or equal to twice mod of t, and which is bounded by some m for every t, for all t belongs to R, but not for all t belongs to R. It's not bounded actually for all t belongs to R in any bounded in any bounded neighborhood of t. If you take any bounded neighborhood of t, you will see twice mod of t is lesser. Suppose you take this interval, say suppose this t is equal to 0, for instance. You take this neighborhood minus 2 to 10. Then this mod of t is okay, it's lesser. Twice mod of t is lesser or equal to 2 times 10, which is equal to 20 in that case. So if you fix any bounded open interval, any bounded interval for this t, and you will see twice mod of t is lesser or equal to. Obviously this m depends on that that bounded interval, okay, which you are choosing here, because in our theorem we need that partial derivative should be bounded by some measurable function in any bounded interval. Okay, so obviously this m depends on the bounded neighborhood of t. bounded neighborhood of T. Or you can say T naught, bounded neighborhood of T naught, where T naught is some fixed point. T naught is some fixed point. And here this our x is actually this x is actually in the interval 0 to 1, so this is also true for all. This x belongs to the interval 0 to 1 because the integration is 0 to 1 actually, so x is in 0 to 1. Okay, this time depends on the neighborhood of that T naught. Now we can apply the theorem for GT. Okay, so what's GT? So we have this g of t, it's actually equal to, so g of t satisfies all the properties of the hypothesis of the previous theorem. So our g of t is this function 0 to t e power minus t square times 1 plus x square divided by 1 plus x square dx. Okay, this is it's 0 to 1 here, not 0 to t, 0 to 1. This is our g of t. So what will be g dash t? It's equal to the 0 to 1, the partial derivative of the inner function actually by previous theorem. So by previous theorem that we have done in previous lecture actually, what's g dash t? G dash t is equal to integral 0 to 1 del by del t of this function e power minus t square times 1 plus x square divided by 1 plus x square, and then we have dx. This is equal to 0 to 1. What's the partial derivative of this function that we have seen already? It's equal to, we go to the previous page, this partial derivative is equal to twice minus twice t power minus t square times 1 plus x square. Okay, it's e power minus twice t e power, next page, it's minus twice t e power minus t square times 1 plus x square then dx. Okay, so this will it's minus 2 times e power minus t square actually, e power okay, what's the partial derivative of this function? It's equal to e power, then the differentiation of the inner function which is equal to minus t square, that's minus 2s t times 1 plus x square. These two will go this. Okay, so it's twice t times, okay, this is equal to integral 0 to 1 minus twice t into e power minus t square into e power minus t square x square dx. So this is integration with respect to t. You can treat with respect to x, you can treat this t as constant here. So it's equal to minus twice t into e power minus t square, then you have integration 0 to 1 e power minus t square x square dx. So you can take, okay, this is sorry, this is this is actually you should take this minus 2t here, minus 2t here. The reason is that you put t square x square by putting t square x square is equal to u square, okay, and you will see this twice t twice x actually, this is t square x square. Okay, twice by putting this and this will be equal to now xt. Okay, by putting equal to xt, just not why I'm taking the square here, is just by putting u equal to tx. Okay, then this you will see this du is equal to t times dx. So therefore if I denote this integral by I, therefore our this I is equal to the integral minus twice e power minus t square. Okay, integral e power minus u square, and then t dx is equal to du. This is our integral, and you can always replace this this is 0 to 1, because you can replace this u by x again. It's equal to minus 2 times e power minus t square. Okay, this is now 0 to 1 e power minus x square dx. So this is the integral that g dash t is this. So this is actually g dash t. Why I am writing this I, it's g dash t actually. So this is your g dash t. So therefore g dash t is equal to this minus 2 times e power minus t square 0 to 1 e power minus x square dx. This is true for all t belongs to R. Okay. Now let's find f dash t plus g dash t. So now f dash t plus g dash t, you will see this, what's f dash t and g dash t. G dash t that you have seen, it's minus twice this, and what is the f dash t that we already calculated here. F dash t, where is this f dash t? Oh, that's this is g dash t. f dash t is g के लिए तो आपके पास ये है. What's f dash t? F dash t we already also calculated f dash t here, but that's not here. Where is this that f dash t? So for g, this is it f dash t, where we have applied the fundamental theorem of calculus. Okay, I think that is raised, I think that one. So f dash t, we have seen that this f dash t is equal to f dash t, it's equal to twice e power t integral 0 to t, no, 0 to t, it's now 0 to, yes, 0 to t e power minus x square dx. And also we have seen in this g dash t, this is this was your f dash t. F dash t, okay. And what's g dash t? G dash t that you are you have seen this g dash t, it's equal minus twice e power t integral it's 0 to t, integral 0 to t. Okay, it's integral 0 to t e power minus x square dx. So this is your g dash t. Okay, where is g dash t? This is g dash t. Oh, by putting this u equal to tx, but what are the limits for u actually? If x is 0, u is 0. If x is 1, u is t. It's t actually. So g dash t is minus 2 e power minus t square 0 to t e power minus x square dx for all t in R, and this one this is g dash t, and this is f dash t. So therefore what will be the sum? F dash t plus g dash t, it's equal to sum of these two integrals. They are equal, and this is a negative sign, it's equal to 0 for all t belongs to R. So that means f of t plus g of t is equal to some constant c. C is a constant, okay, because its derivative is 0. So which means f of 0 plus g of 0 is also the constant c, because it's true for all c, or t belongs to r. But what's f of 0 actually? What's f of 0? You can see this f of 0 plus g of 0 is equal to the integral 0 to 1. So it is integral 0 to 1 divided by 1 plus x square dx. This is f of 0 plus g of 0, and that's equal to c. That's your c. This means c is equal to integration of this, that's tan inverse x, where limits are 0 to 1, but when limits 1, this is tan inverse of 1, that's equal to pi by 4 in fact, because tan is 1 at pi by 4, it's pi by 4, okay. So it means that f of t plus g of t is pi by 4, because at 0 it's pi by 4, but it's constant throughout, and at point 0 its value is pi by 4, therefore at every t its value is pi by 4. So therefore f of t plus g of t is equal to pi by 4 for all t belongs to r. For all t belongs to r. Now we observe that limit 1, this is a very important equation. Now we observe that the mod of e power minus t square times 1 plus x square divided by 1 plus x square, but this numerator is less or equal to 1, so it's less or equal to 1 divided by 1 plus x square. So that means this function is bounded by some integral function. Then we can apply the theorem that we can pause the limit. And the limit of this limit t approach to infinity e power minus t square 1 plus x square divided by 1 plus x. What's this value? This value is equal to this, but t is approaching to infinity, so its value is 0 actually, because it will be e power minus infinity, that's equal to 0. So by previous theorem, this what's g of t actually? G of t is this function. G of t is actually this function that you have already defined here. It's 0 to 1, I think it's 0 to 1 e power minus t square times 1 plus x square divided by 1 plus x square dx. So therefore by previous theorem we can see this limit t approach to infinity g of t, it's equal to limit of this limit t approach to infinity, limit t approach to infinity limit t approach to infinity g of t is equal to limit t approach to infinity integral 0 to 1 e power minus x square times 1 plus x square divided by 1 plus x square dx. And this one we can apply this for f also, not only for g, because f is also bounded by some integral function. So let's see this now. Also we will see this f for the function f. What's f actually? What's f? F of t is equal to integral 0 to t, what's this f? It's equal to integral 0 to t e power minus x square dx whole square. So this is f. So limit t approach to infinity f of t plus g of t, it's equal to limit of this plus limit of this but f of t, you cannot pause the limit for f of t, it's just limit t approach to infinity integral 0 to t e power minus x square dx. Okay, it's whole square plus limit t approach to infinity. This is very crucial step here. It's 0 to 1 e power minus t square times 1 plus x square divided by 1 plus x square dx. Now you see this, if t is approaching infinity, this will be 0 to infinity because limit on that side exists, and this limit also exists. This limit is equal to 0 to, let's keep this limit as it is. Okay, first. Now you will see this limit exists, this one, this also exists because this is pi by 4 throughout, so its limit is also pi by 4 throughout. This limit exists, this limit exists, this one, so that means this limit also exists, but this is the improper integral actually. So you will see this will cube, this cubes. Why this limit exists? Because limit of the integral is equal to integral of this limit, as this function, the integrand function, is bounded by some bounded by some Lebesgue integral function. So we can apply the previous theorem for this function actually, for this integral. Okay, for this integral. So this, for this integral we are applying that theorem, limit of integral is equal to the integral of limit. Not for partial derivative, it's actually the first theorem of the previous lecture. So this gives limit t approach to infinity, f of t plus g of t is pi by 4, and this is limit t approach to infinity integral 0 to t e power minus x square whole square plus this is integral 0 to 1 limit t approach to infinity e power minus t square times 1 plus x square divided by 1 plus x square, then we have dx. This implies pi by 4 is equal to that limit t approach to infinity 0 to t e power minus x square dx whole square plus, but the limit of this is equal to 0, that we have already seen, so it's integral of 0, that's equal to 0. So that means this limit is equal to pi by 4, so which implies that integral 0 to infinity e power minus x square dx whole square is equal to pi by 4, which implies the integral 0 to infinity e power minus x square dx is equal to root of pi divided by 2. So that closes this Euler integral. So thus integral 0 to infinity e power minus x square dx is equal to root of pi divided by 2. So that was our theorem actually. So this is the first integral that we have evaluated with the help of Lebesgue integration theory. Now we have another integral that's also important. Another integral we have, what's that integral? It's for each t belongs to, that's the next theorem. For each t belongs to R. For each t belongs to R, we have this integral 0 to infinity e power minus x square cos of 2xt dx. It's equal to root of pi by 2. Root of pi by 2 into e power minus t square. So for t equal to 0, this is already done. For proof, it's actually generalization of the Euler integral. For t equal to 0, we have seen that integral 0 to infinity e power minus x square cos of 2 cos of 0 is 1, it's just dx, and this we have seen it's equal to root of pi by 2. And if for t equal to 0, this side is equal to root of pi by 2. For t equal to 0, this side is just e power minus x square dx, and this RHS is equal to root of pi by 2, and is already done. Already done. For t equal to 0, so we can assume that our t is positive here. Now let's define the function. Define f of t is equal to 0 to infinity. The integration, the differentiation under integral sign is very important. Actually, this has a lot of applications, because this type of process, by interchanging the limits through integral, this will give the evaluation of some important integrals actually. So because if you see now, let me explain first how it's very important. Okay, let me explain first why it's very important. Because if you prove this integral, 0 to infinity e power minus x square cos of twice xt dx, it's equal to e power minus x square e power minus t. Now let's differentiate this partially with t inside the integral sign. So it will be e power minus x square, this is sine of twice xt, into what's this, the difference of twice xt is, this is actually minus because you are differentiating it, it's 2x. This is equal to e power minus x square minus times e power minus t. So that means you conclude that minus 0 to infinity e power minus x square sine of twice xt, this is twice x here, minus and minus will go, this is equal to e power minus x square into e power minus t, not e power. So no, sorry, this is on this side, it's equal to root of pi by 2 first. This is root of pi by 2 actually, root of pi divided by 2, root of pi divided by 2 with minus sign. So now this is equal to minus times this is equal to just root of pi by 2 here into e power minus t. So but we are not allowed here by using the differential, because here in that case if we take t equal to 0, this will be 0 here, but this will not be equal to 0. So this is not allowed here, this is not actually allowed here. So whenever it's allowed, this will be very beneficial, because you are getting now different integrals by differentiating this function. Cos of 2x xt, it will be sine of 2x twice, so you will get the integral for sine of 2xt. So here it's not allowed. Definitely some problems maybe here, because for a positive it is allowed, then we must have this. But for t equal to 0, this side is equal to 0, and but for t equal to 0, it's equal to root of pi by 2. So how 0 is equal to root of pi by? This is a contradiction. So that means this differentiation of the integral is not equal to integral of the differentiation here in this case. Definitely there is some problem. Okay, so now we define the function to evaluate this integral. Let's come to our main discussion now. Let's define f of t. F of t is equal to 0 to infinity e power minus x square cos of 2xt dx, and we show that this f of t is equal to root of pi by 2 into e power minus t. So the method is that we try to find the differential equation for f of t, then we solve that differential equation for f of t, and we'll get the value of f of t for t belongs to R. For t belongs to R. So since this function, this mod of e power minus x square cos of twice xt, okay, this one, it's less or equal to e power minus x square, and e power minus x square, the improper integral e power minus x square exists by previous theorem. So that improper integral of this also is by comparison test. So which means that, so therefore the improper integral 0 to infinity e power minus x square cos of 2xt dx exists as improper integral 0 to infinity e power minus x square dx exists by previous theorem of this lecture, by previous. So this means that if the improper integral exists, it means that the Lebesgue integral, so the Lebesgue, therefore the Lebesgue integral e power minus x square cos of 2xt d lambda over 0 to infinity also exists, also